Hi, Physics 2, Mr. Janowski. This is the next part of the Chapter 33 slides. Um, so if you remember last time, I cited a lot of things. I talked about Wikipedia. I love Wikipedia. So again, I'll put links to this in the description of this. Highly recommend the entire playlist here. Crash Course Navigating Digital Information. We get a lot of our information digitally now. You ought to know how to navigate it, how to evaluate it, what of that information is good and trustworthy and such. And especially, how do you use Wikipedia? Despite what your English teachers may have told you, Wikipedia is a wonderful and useful thing if you're using it correctly. So, yeah, I'll put links there. So, the other do now questions, back to what we were talking about. What is the work energy theorem? It is sigma W internal, so sum of your internal work, plus sigma W external, sum of your external work. So sum has an SUM. Add up your internal and your external work, and that will give you delta KE, the change in kinetic energy. Second question, what's the first law of thermodynamics? Well, that's the law of conservation of energy. And mathematically, we write it like this. Sigma E initial, sum of your initial energy, plus sigma W external, sum of your external work, equals sigma E final, sum of your final energy. So I like that idea much more. I keep saying that. Add up all of your initial energy plus any work that is giving you more energy or perhaps taking energy away. And that will tell you the sum of your final energy. And again, the work energy theorem and the conservation of energy are mathematically equivalent. They're just kind of different starting points. And I always, prefer the first law of thermodynamics, conservation of energy idea. But again, there is more than one way to skin a cat. You don't always have to do things the same way. There are different ways that will work. So sometimes you might end up using the work energy theorem when you could have used the conservation of energy. It's fine. So what formulas relate work, force, distance, and angle? So these are the two formulas. The top one is work equals the vector F dot, the vector version of displacement. That's the dot product. That's a vector kind of math. You take the physics in college, they'll teach you that there. I don't think anyone in the math department does it here at Charter Arts. I don't think there's a math class where you deal with dot products. So last year in chapter 9, we used the bottom one. Work equals the magnitude of the force times the magnitude of the displacement times cosine theta, which is the angle between them. So the magnitude of force is a vector. The magnitude of force is just the magnitude. So the magnitude of force is just a scalar, and it's a positive number. The magnitude of displacement is a positive number as well, and we call it the distance. Cosine of theta, the angle between them. So evaluate the following. Cosine of 0 degrees, 90 degrees, 180 degrees, and 270 degrees. So depending on how well you like the unit circle, you might know this off the top of your head. You can always just grab your calculator and do it. But here it is. Cosine of 0 degrees is 1. Cosine of 90 is 0. So where are we? Here is 1. Here is 0. Cosine of 270... cosine of 180 degrees is negative 1. Cosine of 270 is 0 again. And then it repeats again and again and again forever and ever. This is a cosine wave. And your value of cosine is always going to vary between positive 1 and negative 1, inclusive. Just keeps going back and forth. So flashback to last year, chapter 9, work and energy. There are 4 important cases to know when you're dealing with force and displacement and whether the work done is positive or negative. So in all of these cases, the displacement is to the right. Our object, whatever it is, has moved and been displaced to the right, and the force is going to be going in different directions. So here's the whole chart. If they're in the same direction, if your force is in the same direction as your displacement, that means the angle theta between them is 0 degrees. Cosine of 0 is 1. And if you're looking at this formula here, that means the work being done there will be positive. If, on the other hand, your object has moved to the right, it has been displaced to the right, the force you're dealing with is to the left. Well, the angle between them is 180. The cosine of that is negative 1. That means negative work will have been done in that case. And so forth and so forth. If the force is at a right angle, 90 degrees, to the displacement, the cosine of that angle is 0. Therefore, that force will have done no work. The force wasn't 0, the displacement wasn't 0, but the work done was 0 because of the angle between them. And then the last case is just the general case. It's not any of these, 0, 180, or 90 kind of cases. It's just any angle. Ask your calculator, what's the cosine of that angle? And it depends if, what it is, whether you get positive, negative work. So also last year, I talked about pushing a book to the right across the table. What forces are acting on the book? So you do a free body diagram. Force applied, that's me pushing it to the right. There's a force of gravity going down. There's a normal force from the table going up. And if it's not a frictionless table, there would be a force of kinetic friction going to the left. So which of these forces do positive, negative, and zero work? To think about this, it is helpful to draw in the displacement vector. So this book has gone to the right. So that's the displacement vector there. That makes it easier to see what the angles are. So in the first case, force applied, 0 degrees, cosine of that is 1. The force I applied to it did positive work. If we're looking at the force of kinetic friction, the angle between the displacement and the force of kinetic friction is 180 degrees, the cosine of which is -1. So that gives you negative work. And then, which we do next? Yeah, the normal force. Okay, the normal force, that's 90 degrees. Cosine of that is 0. So the normal force wasn't 0. The displacement wasn't 0. But the work done by the normal force was 0 because of the angle between them. And ditto that with the work done by gravity. Because the angle here is 90 degrees, or -90, technically. It depends which way you measure it. Because that angle is 90 degrees, the force of gravity does 0 work. So more to now. What do electric field lines around a positive charge look like? So picture a positive charge in electric field lines. Yeah, they go out radially. Nice radial distribution. The lines are pointing outwards. How about around a negative charge? Well, they come in radially. So you can think of the positive charge as pushing the field lines out. The negative charge as pulling the field lines in. If you have multiple charges, it starts to get really complicated. So, it's not just radially out, radially in. Everything's curving. It's a big mess. So question 3, what would the field lines around 2 charged plates look like? So these are not point charges. These are like 2-dimensional plates, basically, is how we treat them. Going back into the page, the field lines around these guys, it gets really messy. There's a lot going on here. It's very complicated. So if we look at this area above the positively charged plate, and again, this is not just a line going across. This is like a plate. Think of a rectangle going back into the page, into the screen. What is the electric field up here? Well, the electric field up there is, one, it's going away. It's going kind of up, but it's also going out to the sides. And it's getting weaker as you're getting further away because the lines are getting further apart. Beneath the negatively charged plate, well, the field is also going up, kind of, but not perfectly up, and it's weaker as you're getting further away from the negatively charged plate. So, the electric field line in either of these regions is much weaker than the electric field between the plates. And how can you tell that? Well, there's a lot more lines between the plates. That means you have a strong electric field. In these regions outside the plates, both above and below, you have far fewer lines, so you have much weaker electric field. That's back from last chapter, chapter 32. How about near the edges of these plates? What is like the magnitude? What is the direction of the field? It's not, it's down sort of from the positive to the negative one, but it's not perfectly down. These things are curving the further out to the edge you get. And they're not constant in magnitude either, because the lines start pretty close together, but they're getting further apart as you're going out. So we call these edge effects. So near the edge of this device, it gets really complicated and weird. How about in the region right between the two plates? Magnitude and direction is very, very constant. The magnitude is straight down, so perpendicular to the plates. You have parallel lines, and they're very evenly spaced, telling you have a strong, because there are a lot of parallel lines, and very even electric field, going from the positive to the negative. So when we're doing this, we're going to say that the electric field between the plates, and this whole volume right here between the plates, is very, very constant. We're going to ignore the weirdness that happens at the edge of the plates out here, and we're going to ignore the electric field that's above the plates and below the plates and all the way out here, way to the sides. We're just ignoring that completely. So here is your equation that relates the potential difference that is applied to these plates. So maybe we hooked up the top plate to the positive terminal of a battery and the bottom plate to the negative terminal of a battery. And the potential difference provided by that battery is delta V in this case. And it relates that to the electric field in this region right between the plates, and D, which is the separation of the plates. It's a distance. So this equation only works for charged plates, which is the point of this slide. So last chapter, we got this formula. This gives you the electric field around a point charge. At the beginning of this chapter, we got this formula for the electric potential, aka the voltage, around a point charge. And both of these equations only work for point charges, and they don't work for charged plates, parallel plates. This bottom equation that we just got on the previous slide, this one works for parallel plates only, and it does not work for point charges. So when you're doing these problems and you see a formula that has all of the right, variables in it to give you the thing you want, you have to make sure that the formula you're using applies to the situation that you've got there. So if we're looking at this, especially the second equation, so delta V is equal to E times D. Solve that for E, electric field, and you get electric field is equal to delta V over D. So delta V will be in volts. D is a distance. It'll be in meters. So what units will you have for electric field? Well, it's going to be volts over meters because you have volts in the numerator, meters in the denominator. So volts per meter are our units for electric field. But try to remember back to last chapter. What were our units for electric field in the last chapter? It was newtons per coulomb. So what's going on here? Time to do some dimensional analysis. This is when you're looking at the units involved in your equations and trying to figure out what's going on there. So we had this formula from earlier in this chapter. Delta V, I think we had it as work equals negative Q delta V, but I rearranged it. So delta V, which is going to be in volts, is equal to negative work over Q. So work has joules, Q has coulombs. That means a volt is a joule per coulomb. And this work formula that we had, work is force times distance. So newtons times meters. So work is joules. That means a joule is a newton times a meter. So start with this idea. I just told you the units of electric field are volts per meter. Okay, a volt is really a joule per coulomb. So now we have joules per coulomb over meters. You can move the C to the bottom. So this guy becomes joules over meters times coulombs. And then over here, we're replacing joules with this idea, newtons times meters. So now I have newtons times meters divided by meters times coulombs. So the meters cancel, and what you're left with is newtons per coulomb. So what that means is a volt per meter is a newton per coulomb. And in this chapter, you can use either one of those as your units for electric field. Now, depending on what equation you're using, it may be more natural to use one or the other, but either one of them is perfectly acceptable. So if the thing is, what's the electric field, and you give me either of those units, they're acceptable. You don't lose half a point. So there is a potential difference of 50 volts between two charged plates separated by 25 millimeters. What is the electric field between the plates? So yeah, we're solving for E, electric field. Put in your numbers. Remember, your denominator is not 25.0 because your denominator needs to be in meters. 25 millimeters is 25 times 10 to the minus third meters. So yeah, keep an eye on your metric prefixes. And that gives you this answer, 2,000 volts per meter, or equivalently, you could have written 2,000 newtons per coulomb. In this case, because of the formula we used, our numerator was in volts, our denominator was in meters. It makes more sense to use volts per meters, but either one of them works fine. So review questions. When do these equations apply, these top two? These apply when you've got point charges, and only when you have point charges. When does the bottom equation apply? Only when you have parallel plates, charged parallel plates. Yeah, that gives you a formula relating the potential difference, meaning the voltage that is being put across those plates, to the electric field in the region between those plates, to the distance d between the plates, separating the plates. So that's it for this part. Yeah, hopefully you found that helpful.